Here we're gonna continue with the analysis of functions and critical points. Now, as a consequence of the mean value theorem, we're gonna see what's called the first derivative tests for critical points. So this is a theorem, and it allows you to classify critical points according to the sign changes of the derivative near a critical point. Remember, a critical point is a point where the derivative doesn't exist, or where the derivative is equal to 0. So now the theorem allows you to say whether the critical point corresponds to a local max or a local min, depending on whether the f prime changes sign from positive to negative or from negative to positive. So let's start with a critical point. Let C be a critical point, of a function f that is defined in some interval. Then the conclusion here is that, well, I mean, there are two situations where we can say something. F prime changes from positive to negative at C. So one side of C is positive, then for slightly higher values than C is negative, then we have local max. So to see this, let's look at a graph of a function. So what's going on here? So this is the critical point C. This is the point where the derivative is 0. So the slope of the tangent line is 0. So there's no change, no infinitesimal change at that point. And let's look at some slopes here. So on the left-hand side, on the left side of C, the derivative is positive. Remember, so the slope is positive. Right, so it's slanted in such a way that the straight line goes upwards. And on the other side we have negative slopes, right? So they smoothly in this example they smoothly transition from one to the other, and that's why the slopes here become less and less positive until they become 0, and then start slowly becoming negative and more negative as you move away from C. And so here f prime is negative on this side. F prime is negative, and and that's why we have a local max. So knowing knowing the sign of f at both sides of a critical point allows you to say whether that corresponds to a local min or a local max. So f prime, now this is the next situation. F prime changes from negative now to positive at the point C. And so we see then we have the opposite situation. F of C corresponds to a local minimum. So and in this situation the graph looks just a mirror reflection about the x-axis of the graph above. And so this is the test. Tests allows you to say something about a function and its critical points based on the knowledge of the value of f prime near the point at both sides. So let's look at what we mean by that. How do we apply this this theorem? Let's analyze the critical points of the function f of x function f of x equals x cubed minus 27x minus 20. So the first thing we need to do here is, so for the solution, in fact the question here is not formally stated, but of course they're asking us to use the first derivative test to classify the critical points. So the first thing we need to do is to find the said critical points. Okay, so we have to find the critical points to be able to say something about them. Okay, so find the critical points. This looks like critical. So critical points. And to find critical points, remember that I mean, I insist on this because people get used to just thinking of critical points as places where the derivative is zero. So I need to stress that many times. Critical points are points where the derivative is either zero or where it doesn't exist. In this particular example, f of x is a polynomial, so that means that it's differentiable everywhere. So critical points are only points where the derivative is zero. But that's just because f is a polynomial. Because f prime of x is equal to 3x squared minus 27, and that's equal to 3 times x squared minus 9, and we have to set that equal to 0. So that implies that the critical points are the values c equals plus or minus 3. So we have two critical points, and now we need to classify them using the first derivative test. So find the sign. We need to find the sign of f prime of x on the intervals between critical points. The intervals between critical points. Okay, so now we need to notice something here that is useful. I mean, from most applications, in particular applications where the function is a polynomial, since it's differentiable everywhere, is continuous, and the derivatives are going to be continuous as well. So f prime cannot change sign between consecutive critical points on the interval between two consecutive critical points, the sign of f prime doesn't change. Okay, so in order to see what the sign is near the point on the left or the right, we look at we have to divide the real line into intervals determined by the critical points, the location of the critical points. So we're going to break the real line here. We have two critical points, minus 3 and 3, and so we have 3 intervals here to analyze. So minus infinity, minus 3, which is the first interval. Then we have the second interval, which goes from minus 3 and 3, so that corresponds to this interval over here. And then lastly, the interval 3, plus infinity. So all the values higher than 3. And at the point minus 3 and 3, the derivative is 0. But in all these intervals, in each one of these intervals, the sign of f is it's gonna remain unchanged. So we just need to pick a test point in each one of these intervals to determine the sign. So in here, f prime of -4, f prime of -4 is equal to, I mean, if you plug -4 into the derivative expression here, the f prime in here, f prime of x, 4 is 16, 16 minus 9 is 7, so 7 times 3 is 21. So that's going to give you 21, and that means that f prime is positive. Since 21 is positive in this interval, f prime is going to be positive in the whole interval. Okay, remember it cannot change sign. So whatever sign it has at any point inside this interval is going to be the same for all the other ones. Okay, so we have another, so we have the next interval here, which is -3 and 3, and we need to pick a point. The easiest point to pick here is 0, f prime at 0, so that gives us 20 minus 27, right? And that's negative, so f prime is negative here, negative inside this interval. Remember, you can pick any point you want, and the signs of the derivatives inside these intervals determined by the critical points, the sign of the derivative in between consecutive critical points is a constant. So the sign of the derivative cannot change in between consecutive critical points. So it just suffices to check. Choose one point here. I chose 0, but you could have chosen, say, 1, which is still in the interval. It's just that evaluating at 0 is more convenient. So, I mean, usually the choice is made so that the computations involved are as easy as possible. And now, so I mean, okay, we computed what happens in between -infinity and -3. And f prime in between -infinity and -3 is always positive, between -3 and 3 is always negative, and for values larger than 3, we have that f prime is going to be positive, because f prime of 4 is the same as f prime of -4. The function is even, so that's going to be equal to 21, and so which is positive, so f prime is going to be positive for values of x greater than 3. And so what's the behavior of f? So what happens? So let me just erase this so we make things more clear to everyone. So before reaching the point -3, the function is increasing because the derivative is positive. Remember what we said? I mean, there was the first application, or the second application of the mean value theorem was that. So you can tell whether a function is increasing or decreasing based on knowledge of the sign of f prime. So since f prime is positive, the function is increasing before -3. The sign of f prime is negative between -3 and 3. So the function is decreasing between -3 and 3. And then the sign of the derivative becomes positive again. And so the derivative, so that implies that the function must be increasing after 3. And so what is the conclusion here then? So based on the first derivative test, or even just paying attention at what the small table here suggests, you're going up before -3 and going down. So that means the -3 must be must correspond to a local max, right? It's a local max, and 3 is exactly the opposite. So you're going down until you reach 3, and then you go up again. So 3 must be a local min, right? So it's a function that goes up, goes down, and goes up again. I mean, this is a typical behavior of all cubic functions. So typically, this is what the cubic functions look. I mean, it's like f of x. It's a cubic function. It's a cubic polynomial. But this is not always the case. Remember the case when f of x is exactly equal to x cubed, where x is exactly equal to x cubed, then the function is just increasing, and it does something like that, something funny like that, where the critical point is 0 meet at the same point, so f prime is 0 at the origin, and the second derivative is 0 as well. So this is kind of a strange situation, and this is kind of a counter example to some of what's called the second derivative test. So we went over today. We're going over is the first derivative test. So we'll discuss this next time, but this is for you to keep in mind. And yeah, okay. So this is the conclusion can be drawn from the knowledge of the behavior of f before and after, immediately after the critical point. Okay, so here minus 3, as we said, the function is increasing before minus 3 and is decreasing after minus 3, and it's, for the same reason, is decreasing up until 3, and then starts increasing again. And so that's what allows us to conclude that minus 3 is a local max and 3 is a local min. Okay, so the thing to keep in mind now is that so this is a note again. So note, let me just write it over here. So when completing this this table, it suffices to choose a test point inside each interval. So we just need to pick one per interval. Here we have 3 intervals, and so we pick a point inside each one of them, and we look at the sign, and that's the sign of f prime there. Again, the sign of f prime remains unchanged in any of these intervals determined by the critical points. And yeah, so that's the first derivative test, and I mean, just to give you a preview what we're going to be discussing in a little while. Remember that f prime tells you whether f increases or decreases, and so analyzing critical points can be made easier in cases where f double prime doesn't vanish at a point, in which case you can tell from the sign of the f double prime what is happening to f prime, to the sign of f prime at a critical point. So if f double prime is positive, it means that f prime is increasing. So if f double prime is continuous, it means that f prime is increasing near a critical point. So that means that since f prime is 0 at the critical point, if it's increasing, it means that the graph of f prime is like this. So you cross 0, so this is where f prime is equal to 0. So it must have been negative before, and it was positive after. So this is this happens if f double prime is positive at this point. And so you change from negative to positive. So that's the situation at 3. So that implies that you have a local min. If f double prime, on the other hand, is negative, then you have the opposite situation. You have the opposite end. So where the function is increasing, then it reaches a local max and then goes down. Okay, so that's what the second derivative test will tell us. But there are some times where that cannot tell us anything because f double prime vanishes. Just in the example I gave you of x cubed. Function is increasing, but f double prime, say at the critical point is zero. So, but the first derivative test always works. Okay, so that's one thing you need to keep in mind. So if you want to find out whether you have a local max or a local min, if they ask you to use the second derivative test, it means that you're not in that situation or not in the situation where f double prime is zero at the point. But if they don't ask you to do that, I mean, you can analyze or you can use the sign of f prime to analyze the function and the critical point, which always works. So that's it for this video.